New stuff. Okay. I want to move from abelian to non-abelian. Now, we have examples of non-abelian operations already, but they're not trivial. So I'd rather make a couple of generalized decisions and then develop a new example. So let me talk about some notational conventions. Continually writing star is a pain in the neck. So I don't want to use star. What I'm going to do, though, is I'm either going to use plus or times, just by default. And most of the time, actually, instead of writing multiplication with a symbol of any type, instead of writing A dot B or A cross B, I'll just write AB. That's multiplication. And I'll call them sum or product. It'll make my life easier. But I'm going to default to using addition in abelian situations. And as we saw on Thursday, since my favorite example is the integers mod n, makes sense to use addition mod n as my headspace canonical operation. So when I'm dealing with abelian groups, I'm going to write them in additive notation. And that means more often than not, I'll use a product if I know it's non-abelian or I don't know. Now that means I can go prove that a group is non-abelian and use multiplication, or I can, in multiplicative notation, prove that my group is abelian. It's going to depend on what I end up with. Additionally, if I'm using numbers for my elements, then I'm going to have an identity of 0 and 1. Because if I'm dealing with multiplication, those make sense. If I'm dealing with addition, those make sense. But if I don't have numbers involved, I'll stick to E. Things like matrices, they have their own symbol for an identity matrix, right? Capital I. Once I have a symbol defined, then I can work with it. If I'm thinking about my operation, well, wait a minute. Operation, identity, inverses. If I'm in an additive notation, what should I use for the inverse? If I'm thinking in this universe over here, in adding, Say again?
The negative.
The negative. That makes sense. But if I'm in a multiplicative notation, then minus is not the right symbol. But now I start thinking about some of the stuff we did back in discrete. And I remember we tried to solve equations in the integers mod n, right? 3x equals 5 mod 12 or something like that. We figured out when we could and when we couldn't. But I didn't use 1 over because we couldn't divide in that universe. So over here, I'll use that inverse notation, which jives with what I saw in matrices, capital A inverse, using that -1 power. So these are conventions for the way we write things. One of the homework questions asked you about a group with a finite number of elements, and then asked you to look at what happens, show that one of them ends up being the identity at some point. A to the k equals e for some k. There's one in this section, right? Or is that on the next section? Which one? The one you just turned, okay. But the way it was written in multiplicative notation, right? It was written for any group. And they said, I'm going to repeatedly do my operation. So if I were doing my repeated operations, in the additive universe, it would look like that. And in the multiplicative universe, it would look like that. What's my shorthand on the right for repeatedly multiplying? I can write a power. Here's where I run into an issue. Over here on the right, what's my shorthand on that side? I'm sorry, over on the left. Whoa.
Times n.
But there isn't multiplication in that universe, is there? That's my problem. We only have an operation, one operation in a group. And by default, in this group, that operation is addition. So if I write this as NA, that's going to look weird in a universe where multiplication doesn't exist. This makes me personally kind of crazy, especially if that group contains numbers. Because then it looks like I should be multiplying. But I'm not allowed to multiply, I'm only allowed to add. I'll run with it. That's the correct shorthand. I just don't like it. Multiplication is easier if my group is containing numbers, even if I'm thinking of it as repeated addition. I believe it's on page 40. Check. There's a summative table with all of this information in the text. Yes. Please notice, down at the bottom there, we see distributive rules. In a group, distribution works. Because repeatedly, NAs and MAs, if I add those together, I have n plus n of them, right? I just do one set of operations after the other. In multiplication, that becomes adding and multiplying of powers, opposed to coefficients. But they mean the same thing, depending on the way we write our group. And that's really the kick in the pants, is that there is only one operation in any given group. If I want to deal with two operations, I'm going to have to move to a different structure. I'm going to have some idea about the way those two operations relate to each other. Groups only have one operation. I keep referring to the order of the group, how many elements are in it. Let me give you a symbol for that. And we'll call that the order of the group. Which jives with our order of a graph, doesn't it? Questions? Okay. I want to build for you a brand new non-abelian example. And this example is going to stick with us for most of the rest of the term. We can do this for infinite sets. I'm not going to in this course. Chapter 2, Section 4, discrete math. What's a permutation? I know it's evil. I keep asking you to remember this crap.
This is the NPR, but there's like, I know there's a formula for it with the explanation formula. I can't remember what it is.
But that is that permutation, same word, is a counting method. That's not a permutation of a set. That's a permutation of subsets. That's a different thing, but that is the same term. And this is another annoying piece in math. Not only we use the same symbols over and over and over again, we use the same words and they mean different things in different contexts. That is actually in chapter 6 in the discrete book, which is why I specifically mentioned chapter 2, just so I could pull you out of that one. But that's all the problem in stats talks about permutations as counting. You're right. But that's not the way I want to use it here. Permutation is a one-to-one and onto function from the set to itself. Now, this is why I said it doesn't have to be a finite set, because any one-to-one and onto function in the reals is a permutation of R. Any one-to-one and onto function of the integers is a permutation of the integers. So here's a really easy example with with an infinite set. By the way, this could just as easily go from R to R. How do I know that this function is one-to-one?
Integer only has one negative of itself.
If I say, hey, minus x equals minus y, multiplied by minus 1 on both sides, then x must be equal to y. That's my proof. How do I know it's onto?
Because all of the outputs are within the codomain, so within 7 integers, right?
I think I know where you're getting, but I believe you actually said it exactly backwards. I want to say that every element in the codomain is part of the range.
Right.
As opposed to every element of the range is part of the codomain, because the range is always a subset of the codomain. I want to say that it's the whole thing. How do I show that?
Every input has a unique output.
Again, I think you just said it backwards as well. That's the definition of a function, that every input has one and only one output. I want to show that every output, every element in that codomain set has an input. In other words, no matter what number you get out, it's the negative of some number, right? So if you pick a number, W, then it came from minus W, right? Because minus and minus is a plus. I have to be able to show that every output can be hit, that I can be on everything in the output set. That's why we call it an onto idea. And we're going from the set to itself. There's an analysis way to do this too. This function is monotone in decreasing. Minus x, right? Every monotone function is 1 to 1. Every monotone function that is infinite is onto. And you can do that proof with the stuff you've already seen in 207. I love linking my classes together. They work perfectly in sync with one another. Surprise. But I was talking about a finite set, right? So, somebody give me a number. Moderately small positive number. 2. 2 is going to be really easy. So, let's suppose I have a finite set with only 2 things in it. A permutation on this set is a function from the set to itself, right? So, let's define a function that's a permutation. List the inputs, list the outputs. Well, if those are your inputs, what are your options for outputs? Zero and 1. Which one goes to which one? Great. So here is a permutation. But there's another permutation that's possible as well, right? Or that one. It turns out that with only 2 elements, those are the only possible permutations, right? If I have more elements in my set, then I have more options, right? Rather than write columns, I'm going to write a row. So let's consider the permutation where 1 goes to 4, 2 goes to itself, 3 goes to 5, 4 goes to 3, and 5 goes to 1. This is a permutation. As a matter of fact, I'm going to write it more often like this. So I'll just write it as 2 rows with the from on top and the 2 on the bottom. That's called, to no one's surprise, I hope, that's called 2-row notation. Surprise. I'm going to name this permutation. I name those functions f, right? Typically, permutations are given lowercase Greek letters. So I'm going to call this particular permutation sigma. That's a function. Here's another one. Notice the top row stays the same, so it's really only the bottom row that matters. But here's another function, which I will call tau. And tau is, bottom row is 3, 5, 4, 2, 1. These are objects in the set of permutations on 5 things. Right? If I had any set with 5 objects, and I looked at all the different possible functions, I only had 2 objects, I only had 2 choices. But here I have 5 objects, there are a lot more choices, aren't there? I wonder how many. I'm not going to answer that question right now, but let's think about that for a little bit. We'll come back to it. I could write down that bottom row in any order I want, and that would be a permutation as long as it's 1 to 1. So I can't repeat a number, and it's on 2, I have to have all 5 numbers down. Yes? Those are functions. An operation on functions that results in another function from the same set to the same set, right? Both of those functions go from S to S. So if first I did one and then I did the other, wouldn't I still be going from S to S? I go from the set 1 to 5 to set 1 to 5 using sigma. I go from the set 1 to 5 to the set 1 to 5 by doing tau. I did sigma first, then tau. Wait a minute. Algebra class, pre-calc, calc, what do we call doing one function after another?
Composition.
It is a composition. And as a matter of fact, one of the things we wrote down but didn't prove was that composition is associative. That was a theorem we wrote down earlier last week. So I know that works, it's closed, it's associative. I'll have to figure out the rest of it in a bit. Function composition would mean I would do one function and then the other, right? And I got to plug in numbers. So I'm going to say that this is acting on some number. So if I were to put in 1, what would I get if I did tau composed with sigma of 1?
Wait, no, you get 5.
How?
Because tau goes from 1 to 3, and then you take sigma and go from 3 to 5.
Oops. we see that little circle, we do tau of sigma of 1. I have to do sigma first. Inside to outside, not outside to inside, right?
Yeah.
So I do sigma of 1. 1 goes to 4. And then I do tau of 4. 4 goes to 2. But if I do sigma of tau of 1, what do I get? Aha. This operation, composition of functions, is not commutative. Okay, wait a second. Wait a second. If I'm thinking of this as an operation, we only did it on the number 1, but the permutation acts on the whole set of objects, right? So let's consider, how would we do tau of sigma? And write that like this. Well, we already know tau of sigma of 1 is 2. That's what we did right here. So we have to do this 4 more times for the numbers 2, 3, 4, and 5, yes? So I pull back the sheet a little, and I look at 2. I go from right to left here. I do sigma first. So what's sigma of 2? 2. Tau of 2 is 5. Sigma of 3. 3 goes to 5. Tau of 5 is 1. 4. Sigma of 4 is 3. Tau of 3 is 4. 4 goes to itself. 5 goes to 1. 1 goes to 3. So tau composed with sigma is that. What's sigma composed with tau?
Five, 1, 3, 2, 4.
That's what I have as well. Perfect. Wonderful. I love it. If we think of this operation as a multiplication, not appealing. So, here's what I want to claim. For any finite set, I'm going to write S sub A as the permutations on A. This is a group. Under this operation of composition, this is a group. If the first one goes from the set A to the set A, and the second one goes from the set A to the set A, and they're both one-to-one and they're both onto, then the composition is one-to-one and onto. Again, I showed that in discrete, but I can prove it directly. And since it's composition of functions, we know it's associative. What are the two other things I need? Make this a group.
Your identity and inverse.
The identity and the inverse. I got to do the identity first. So what's the identity? What function could I compose with? E composed with sigma gives me sigma. Sigma composed with E gives me sigma.
This composition, that's just, say it's just 1 to 1, 2 to 2.
E of I is equal to I. How do I get inverses? Again, I push you back to discrete, where we did diagrams for functions with arrows, right? That was the way we wrote that diagram for sigma in the first place, back here. How do I find the inverse of this? Say that out loud. No.
Go from the two.
Turn the arrows around, right? So all I have to do is switch the rows. Wait a minute, that means I know what sigma inverse is, right? If we look back at sigma, 1, 2, 3, 4, 5 across the top, 4, 2, 5, 3, 1 across the bottom, then sigma inverse is 1 goes to 5, 2 goes to 2, 3 goes to 4, 4 goes to 1, 5 goes to 3. And we can check that if you do sigma followed by sigma inverse, you're going to get the identity, right? Pick any number in sigma. 3 goes to 5, 5 goes back to 3, so 3 goes to 3. Sigma times sigma inverse gives me the identity. I have a group. Now, since only the number of things in my set matter, I've been using the numbers from 1 to n. When I have a finite set, the collection of permutations on n things is known as Sn. And for reasons that will be discussed in a little while, we're going to call this the symmetric group on n letters, symbols, on n objects. So our sigma and tau were part of the group S5. And we know that sigma tau is not the same as tau sigma. S5 is not abelian. Matter of fact, Sn is not abelian. Questions?
So do functions have to have like a defined equation, or can it just be something like that?
I don't have to be able to write my function as a function of a variable,
Okay.
especially on a finite set. I can just enumerate all the values, and that's really what this is. Like the function from you to your cell phone, right? I'm not going to be able to write a formula that if I put in Reese McCulloch, it's going to give me your cell phone number, but I can make a table. And I say, oh, f of Reese is this number. That's all this two-row notation is it's a table for my function.
Okay.
There are other ways to write permutations. We'll get there. Give me a little bit. Other questions? Now let's see if we can answer this question. How many things are in Sn? How many one-to-one and on-to functions can we write? How many different tables can we write? Where the left column or the top row is 1 through n, bottom row we need to fill in. How many different ways can we do that?
How many like I'm trying to word this right. An element to like n. So if there's like 5 elements, it'd be like 5 to the 5 power. So there'd be like 25 different outputs.
But 5 to the 5 is much bigger than 25.
You're 100% correct.
And that's going to give me a crap ton more things. But let's think about the way that would work, right? If I'm looking at S5, or even if I'm looking at S2, because we started with S2, right? I want to know how many ways you can fill in those blanks. Now, what you said is 5 to the 5th, right? Which means 5 in the first spot, 5 in the second spot, 5 in the... But that would allow me to repeat things, wouldn't it? My function wouldn't be one-to-one anymore. And?
The 5 factor root.
Because I could have 5 choices here, And then I can't use that one again, so there are only 4 options there. I can't use either of those, so there's only 3 options here. I can't use any of those. I can't use it. Aha. And if we were looking at S2, I used 0 and 1, but now I would want to use 1 and 2. Then there would only be 2 options here and 1 option there, 2 factorial options. How big is Sn if I generalize this? It most certainly should be. Now that means that 5 factorial is already 120. 6 factorial is 720. 10 factorial is 3.6 million. These groups are huge. S4 has 24 things in it. That's not a small number of objects. Yes, question? Questions? Every time I write a permutation in 2-row notation, the top row is always the same, isn't it? No matter what I'm doing, the top row is the same. Why am I wasting my time writing the top row? Shouldn't I really just need the bottom row? In a sense, no, that's how you gave me tau times sigma. You just read off the bottom row because we knew what the top row was. That makes sense. So here's a permutation. In S8. This acts on the pieces in the 8 universe, right? Only the numbers 1 through 8 exist. I've heard that phrase before. When we were talking about Zn, I said, imagine a clock that only has those numbers on it, right? And then we said, this is the entire universe, and we're going to add and multiply and look at inverses in this. Let's consider what happens to all the different numbers I'm using here. And let's iterate through this process. Somebody pick any number you want between 1 and 8 and repeatedly apply sigma to that number. So, what's your number of choice? 5 goes to 4 goes to 7 goes to
5.
I've got a closed loop, don't I? 5 to 7 to 4 to 5 to 7 to 4 to 5 to 7. I've got a cycle inside this. Nope, I wrote that backwards. 5 goes to 4, 4 goes to 7, 7. I even drew it like a little wheel. Now, clearly, I've not exhausted all the numbers between 1 to 8, so pick a number that's not listed there. 1. What happens to 1? 1 goes to 3. 3 goes to 6 goes to what's left? Pick a number that's not there. But 2. 2 goes to 8. Goes back to 2. These are the cycles in sigma. So let's consider, instead of writing these as wheels, let's write them as lines. I'm just going to write the numbers in order and assume that when I get to the end, I wrap back around. So instead of writing 5, 4, 7 like this, I'm going to write 5, 4, 7 like that. And I can think of every time I do this, I march 1 unit to the right. And then I would have another cycle here. 1 goes to 3, goes to 6. And I have another cycle here. 2 goes to 8, back and forth. So this is called the cycle notation for sigma. A cycle must have 2 or more numbers in it. So if I have a number that goes to itself, I don't even bother to write it down. Here's tau. Turn tau into cycles. What is the cycle notation for tau?
1, 2, 3, 5, 4, 7, 6, 8.
Almost. Cycles of length 1 don't get written down. Those are fixed points, right? 6 goes to itself, 8 goes to itself. I don't even need to write that nothing's changing with that. Yes? Please note, Ben, you decided to start all the way on the left and just work your way to the right in here. That's how you came up with these cycles in this order. These cycles are disjoint from one another. No numbers show up in more than one cycle, right? Every permutation can be written as a product of disjoint cycles. That makes sense, right? No matter what permutation you have, you'll look at which numbers go to which and you'll get loops. And if a number's not in a given loop, it's got to be somewhere else in a different loop. This is a partition of the elements in our set A. What I'm doing to 1 and 2, switching them back and forth every time I do tau, does that affect what I'm doing to 5 and 3 and 5? One and 2 doesn't care what 3 and 5 are doing, right? 3 and 5 doesn't care about what 4 and 7 are doing. None of them care about 6. Disjoint cycles can be written in any order you want. So I could just as easily write this like that. Disjoint cycles are order independent. Questions? So far, so good. Cycles of length 2 get used a lot. So they get a special name. We call them transpositions. But most of the cycles of length whatever, the length is the number of things in that set of parentheses. So in tau, all of my cycles are of length 2. Back in sigma, we had 2 cycles of length 3 and 1 transposition. Okay? I could do sigma followed by tau, right? Tau times sigma, tau composed with sigma. That means I can do one cycle after another, even if they're not disjoint. And if I'm doing composition like I'm doing, if I'm doing multiplication as if it were composition here with cycles, I've got to work right to left, not left to right, because I do the inside function, the right function, before I do the left function. What does that mean? Here are 2 transpositions. And for the hell of it, I'm just going to say these are both in S3. So there are no numbers 4 or bigger that I need to worry about at the moment. I would like you to write those. Sigma tau and tau sigma. Well, sigma tau would be 1, 3, then 1, 2, right? I'm going to multiply these together. That means first I'm going to do tau because it's on the left, on the right, and then I'm going to do sigma because it's on the right. So how does this work? Well, if I was thinking of this in 2-row notation, I'd say you put in 1, see where it goes. Then look at the next one and see where it goes, right? This cycle 1, 3 is really short for 1 goes to 3, 3 goes to 1, and 2 is left alone. This cycle 1, 2 is short for 1 goes to 2, 2 goes to 1, and 3 is left alone. So there they are in 2-row notation as well as in cycle notation. Given what you've already seen, it's probably easier to follow what I'm going to say in the 2-row notation. But let's think about it in the cycle notation. I take 1 and I put it in. Put it in here, 1 goes to 2. Now I have 2, which I stick in here, and 2 goes nowhere. So 1 goes to 2. What happens to 2? I put 2 in, 2 goes to 1. Now I have 1. I put 1 in, 1 goes to 3. 2 goes to 3. What happens to 3? Nothing. So I still have 3. 3 goes to 1. Now, if you don't like the way I did that, moving my finger from right to left here, let's do it here. Tau, 1 goes to 2, 2 goes to 2. So 1 goes to 2. 2 goes to 1, 1 goes to 3, so 2 goes to 3. 3 goes to 3, 3 goes to 1. There's the 2-row of the same calculation. This group is not abelian. What happens when I do tau sigma? If you want to do this in the two-row notation, you can do that in the two-row notation. But it will be eventually, I believe, faster to do it in cycles. You have to talk through it each time when you do the cycles. So what happens for tau sigma?
The first one goes to 3.
And then 3 goes nowhere. So 1 goes to 3. So now let's look at what happens to 3. 3 goes to 1. 1 goes to 2. So 3 is going to go to 2. What happens to 2? Wait a minute. 2 goes nowhere and then?
And then 2 becomes 1.
One goes to 3, 2 goes to 1, 3 goes to 2. Those are different permutations, aren't they? This is a non-abelian group. The order in which I do the multiplication, the arithmetic, the composition matters a lot. Try a larger example. One, 3, 5, 2, 6 multiplied by 1, 2, 4, 3, 6. In S6. Now, by default, because I think of this as living in S6, I know I'm going to have to look at what happens to 1 and 2 and 3 and 4 and 5 and 6. I almost always start at 1. You don't have to. You can start any bloody where you want. I'm almost always going to start at 1. Just to see what happens. So, right to left, what happens to 1?
Would be 1 going to 2? No.
1 goes to 2 here.
Yeah. And 2 goes to 2.
Oh, 2 goes where here?
Oh. I didn't see that.
2 goes to 6 here. So 1 ends up on 6. Well, now I don't have to look at 2 next. I have to look at 6 next, because that's where I ended up. Remember, I'm going to keep working my way through the cycle. So I'm in the right one, 6. Where's 6 go? 6 goes to 1 as we wrap around. What happens to 1 on the left?
3.
In the right, 3. 3 goes to 6. In the left, 6 goes to 1. Wait a minute. 3 goes to 1 goes to, did I write something down? 1. Oh, yes, I did. Okay, so we'll keep going. 3 goes to 6, 6 goes to 1, we're closed. That's it. 1 goes to 6, 6 goes to 3, 3 goes back to 1. That's all I get out of this cycle. Which means I need to look at the other numbers. So 2 or 4 or 5. Where do you want to start? 2. What happens to 2? 2 goes to 4 here. Then 4 goes nowhere here, so it goes to 4. So what happens to 4? And then 3 goes to What happens to 5?
Because it's, you know,
It goes to itself here, which means we end up at 2 and we close back around. By the way, the reason I jumped is because I did copy this incorrectly from my own notes. My own notes have the left one being 153. I wrote it down wrong, so the answer doesn't match, and I freaked out. Wait, no, I made a copy error, but we still managed to figure it out. And that's the best part. Questions?
we always go right to left.
When we are multiplying, yes, we always work from right to left. Even if we have more than one of these, more than 2, right? The following is ugly and is taken directly from the textbook, provided I copy it down right. 1, 5, 2, 4, 1, 4, 3, 2, 5, 4, 2, 1. I'm pretty sure I can leave this in S5 or S6, but I don't see any 6s, so 6 isn't going to get affected by anything here, right? What happens to 1? 1 goes to 4. Nothing happens to 4. 4 goes to 3. Nothing happens to 3. Nothing happens to 3. So 1 goes to 3. See how I worked from right to left all the way through that? Now I'm at 3. Work from right to left. What happens to 3? Itself.
So
1. So 3 goes to 5. What happens to 5? What happens to 4? Which means the only thing I don't know about right now is 2. I hope so, because otherwise we have a problem, right? So 2 should go to itself. Let's find out. 2 goes to 1. 1 goes to 4. 4 goes back to 2. 2 does go to itself. It's a fixed point of this function. Questions?
I think it's easier to like go about doing this way to break them all up into 2 rows.
I think 2-row gets really tedious after a while. I like working in cycles. I think they're faster once you understand how a cycle works. And that's going to take some getting used to. So I would start in 2-row, just so you can see how it all works over and over, and then do them again in cycle. This is unfortunately something that is not intuitively obvious. But there's a benefit to working in cycles that is a little more difficult than working in 2-row. So let's consider this permutation that we came up with here, 1, 3, 5, 4. What's the inverse of that? Now in 2-row notation, Reese, I'd have to write this out. 1, 2, 3, 4, 5. I got to write it in the right order, damn it. 1 goes to 3, 2 is fixed, 3 goes to 5, 4 goes to 1, 5 goes to 4. To do the inverse, I flip the rows, and then I have to rearrange it so that the top is in the right order. Right? 1 goes to 4, 2 goes to 2, 3 goes to 1, 4 goes to 5, and 5 goes to 3. reading it bottom to top, over here on the left. In cycle notation, all I have to do is go backwards. And because the order in which I write the loop doesn't matter, I could just as easily write this like that. Because I said as we did this cycle, we went 1 unit to the right and then we wrapped around. So I want to go 1 unit to the left and then wrap around. Just have to write them in the other order. Here's what I'm saying. This is why I like cycles. Because every transposition is its own inverse. Yes.
Could you explain that one more time?
Okay, so in cycle notation or in the two row?
Cycle notation.
Okay, so this says 1 goes to 3, 3 goes to 5, 5 goes to 4, 4 goes back to 1. To go the other way, 4 should go to 5, 5 should go to 3, 3 should go to 1, and then 1 should go back around. So I write it 4 to 5, 5 to 3, 3 to 1, back around. But I don't have to start with 4. I can start with any of these numbers. So I can start with 1. 1 goes to 4, 4 to 5, 5 to 3, back around.
So like the 4 to 5,
This.
5 to 3, 3 to 1.
Yes.
That's correct. And that
Yes. This is an option. You don't have to do that.
Okay, yeah.
But think about a transposition. A transposition says switch A and B. If you want to undo that, don't you just switch A and B? It's its own inverse. Now, I will freely admit, as we get more and more and more of these things, even just looking at S3, how many things are in S3? Which is 6. Now, one of those things is the identity, right? The identity definitely lives there. But then I have 5 other things. And I can write all the permutations out. I can write them in two-row notation. There's the identity. I can write that one. This one. And that one. Those are transpositions, aren't they? Notice that first one switches 2 and 3, but leaves 1 alone. So this in cycle notation is 2, 3. What's the next one?
1, 3.
1, 3. And the one after that? But those are not my only options, because there must be at least 2 more. Well, there must be exactly 2 more, right? Because we only have 6 of them. There have to be a total of 6. But I've seen the other 2.
I forget if we talked about this already. Does it matter if you, like, for example, for that third one, that's 1, 2, 2, 1, 3, 3, 8. Does it matter if you start at the 2 instead and go 2 to 1 and write it 2, comma 1?
Nope, because the transposition, the
Right.
order, I've just written the smaller number first.
Okay.
Your choice. What are these 2?
We want to.
There we go. 312.
2, 3, 1.
That's the top one and the bottom one right here. That's these two. 312 or 213. But we wrote those in cycle notation and in 2 row. So I have that. I could say, you have 6 things. You need to make a table for me of what happens when you take any of those 6 and multiply them by any of the other 6. We'd be here a while. Put a bookmark on page 46. Please note that this book did not use E for the identity. It used a lowercase I. Funky little I shape here. I hate that. I'm going to use E because I always screams complex number to me and I don't want to mess with myself. I am a visual mathematician. So I'm going to cheat. Remembering these like this pisses me off. Here's a triangle. Please notice that I have a triangle that I cut out of the piece of paper. I've numbered all 3 corners. Right now, they all match, don't they? Pick the triangle up, twist it, turn it, rotate it, flip it over, don't scrunch it up, put it back in the hole. I'm going to get one of these. If I pick it up and put it right back down, then I've got the identity. Nothing changed. What if I want to switch 2 and 3 but leave 1 alone? Pick it up, turn it over, 2 and 3 are switched. What if I want this one? 1 goes to 2, 2 goes to 3, 3 goes to 1. Do that again, Jalen. I turn it 120 degrees. What if I want this one? 1 goes to 3, 3 goes to 2, 2 goes to 1. I turn it again. One goes to 3, 3 goes to 2, 2 goes to 1, inside to outside, right? Matching the inside. Holy shit. Given any regular polygon, you can do this sort of behavior. These interchanges are flips, like you drew a mirror on your shape. So I'm going to call this one mirror number 1 because it's the mirror that fixes 1. And this is mirror number 2. And this is mirror number 3. And this is rotation 1 and rotation 2. This particular group is called a dihedral group. And in this case, that's just another name for S3, D3. But D3 is the same as S3. D4 is not the same as S4. The size of Dn is 2n. There are n rotations and n mirrors. And my challenge to you is to see what happens with a square. That would be D4, wouldn't it? I claim there are only 8 things in this group. Now, again, I could then build a table for these groups. Again, I'm not going to, the textbook has it. But D4 is a square. I will see you all on Thursday. Have a wonderful rest of your day. My reason, by the way, for learning about dihedral groups in the first place was inorganic chemistry, crystal structures. None of this was abstract to me when I learned it.